Hello friends, welcome again. In the last lecture, we discussed about second order system, specifically for the mass spring damper system. Let us simulate that system in MATLAB using different methodologies. So I've considered few values here. Time I've considered from 0 to 4 seconds with a frequency of 0.01. Mass is 18 kgs. Stiffness K 70. I'm converting it into newtons into 9.81. Similarly, damping 6 into 9.81. And the force, I'm assuming it to be 5 kgs. So in newtons, it will be 5 into 9.81. And the system, I am representing it as a transfer function. So TF represents for transfer function. Now let me write here help TF, the syntax for transfer function. So TF numerator comma denominator. So in numerator we have 1. If you see the equation here for the transfer function that we had derived earlier. So in numerator we have 1 and in denominator we have m into s square plus cs plus ks. So here the coefficient for s square is m. Similarly, coefficient for s is c, and similarly for coefficient of s to the power 0 is ks, that we have represented here m comma c comma k. M comma c comma k, I am representing here it as k instead of ks. Then I am defining the input u equals to f into ones of size of t. Now if I let me just remove the semicolon from here and run this. So here the system is represented in a transfer function form. Here 1 upon 18 s square plus 58.86 s plus 686.7. This is a continuous time transfer function. And u is again now here as a vector, which is nothing but f into ones of size of t. So what is size of t here? You can see here from the workspace it is 401. So I'm multiplying that vector with 1, that is ones, into f. Here f is nothing but 5 into 9.81. Now the first step that we do here is for plotting this unit step response. Let me just clear it. I'm representing it as figure 1, step of SYS. Let me just run this code. So this is what the amplitude of a mass spring damper system is, the displacement. It is going up to 1.5 into 10 to the power minus 3 in about 4 seconds. So here input, this is a unit step input. And if you want to see the parameters here, what is the peak time, you can find that by writing the syntax here, step info SYS. Here you can see we have rise time, transient time, settling times, maximum settling time, and peak time. You can also view in the figure. Here the peak response is about 0.535 seconds. Here we have 0.535 seconds. Similarly, rise time is 0.208, 0.2078, it is approximately 0.208 seconds. Similarly, we have settling time. Settling time is 2.27 seconds. So this is how we can plot a unit step response by using step command. Again, if you want to explore this, you can simply write here help and sys, and you can have the information readily available here. Now let us proceed further. Now instead of unit step response, I want to see the simulated response, with different control input, that is, it will not be a unit step response. So this can be represented, it can be simulated using the command lsim. Lsim, we have already, if you have been practicing MATLAB simulating example before, you must be aware of this command lsim. Else, let me give you a brief overview of this lsim command. So it computes the time response simulation data of dynamic system to arbitrary inputs. So this MATLAB function returns the system response y to the input u sampled at the same times t as the input. So the syntax is lsim, that is system, then followed by input, then followed by time. So the system is represented, I have represented it as sys, that is what we can see here, sys. Input is u, I mentioned input here u, which is a vector, and time, and the output will be your states, that is position and velocity, and the time t out. So we'll get y and t as the output vectors, and this I am representing this in a figure 2. So plot t comma t underscore out comma y comma b represents the color of the lines, and the line width I would given it as 1.5. Title I mentioned as displacement versus time for spring mass damper system. X axis represents time and y of course represents the displacements, x or in meters. Now let me run this code. Now see here we almost get a similar response here. Let me uncheck these variables. All right. So now here we observe we get almost a similar response here. Now one thing here, students get confused about why there is a difference in magnitude in the responses of the amplitude, that is the displacement. Well, the reason is where input is not a unit step input in this case. Now if I give a unit step input, let me uncomment this. I am pressing Ctrl T. I am commenting this line. Now here input is 1. Now if I run this code, so now we can see now even the magnitudes are matching. So that means we are getting the same amplitude or the displacement x in meters. Now after this, how do we plot velocity? So there are multiple ways. So let us try one of the methods. To find the velocity, we multiply the displacement transfer function by s. S is nothing but the Laplace variable, which corresponds to differentiation in Laplace domain. Thus transfer function for velocity becomes So what we do is we multiply S with the displacement transfer function. What is displacement transfer function? This one, 1 by ms square plus cs plus ks. So I am representing the transfer function for velocity as gv of s into 1 upon ms square plus cs plus k s upon ms square plus cs plus k. Now let us switch to MATLAB again. Now see here, transfer function for velocity. So here numerator is now 1 comma 0. So here in numerator we have the coefficient of s is 1 and s to the power 0 is 0. So their coefficient for numerators are 1 and 0, which in vector form we can represent in these closed brackets. And the denominator is again m, c and k, which remains same, denominator of the transfer function. Now the system again transfer function, we have to represent it by using the command, the syntax tf. I have changed the variable name to sys underscore v equals to tf numerator comma denominator. Then finally we do the same process. We follow the same process here, simulate the velocity response. Here output I have represented it as velocity and the t output vectors is velocity and t, and I've again used lsim syntax here, sys underscore v, which is this variable, comma the input u, comma time variable t. And finally I'm plotting, I'm naming that figure as figure 3. Plot x comma y. In x variable we have t, which is this t out, and in y we have velocity. B again represents the color of the line, and the line width I am considering as 1.5 so that it is clearly visible. Title is velocity versus time for spring mass damper system. X label, in x axis we have time and y we have velocity. Now let me run this code. Now see here, now we have that velocity is actually approaching towards 0. So this is how you plot a velocity curve for a mass spring damper system. In fact, for any other uh, system we can use it. Now there is another method we can obtain the velocity. Of course, the velocity it is represented as v equals to dx upon dt. Now what is x? X we have actually found here in our previous lectures. Let me just go back to MATLAB. What we'll do is we'll differentiate that equation directly in MATLAB. So x is k into f 1 minus omega n by omega d. I think that equation is this one. It's equation number 9. So here y of t is a into k. Here a was representing the input force. So in our case we have considered f. So it is f into k. F into k into 1 minus omega n by omega d. 1 minus omega n by omega d into e to the power of minus zeta omega n t into e to the power of minus zeta omega n into t to sine of omega d t plus phi. Sine of omega d t plus phi. So if you notice here, I have written dot here because here time is actually a vector. So we need an element to element multiplication. That is why I have written here dot. Otherwise, MATLAB will simply throw an error. And what is omega n and omega d? Omega n is square root of k by m. That is why we were going in detail about these expressions in the earlier lectures. So omega n is under square root of k by m. I have represented it here ks by k. Then zeta is c by square root of 2 into m into k, c by 2 into square root of k into m, and omega d is omega n into square root of 1 minus zeta square. we had written omega d earlier. This one, equation number 7. So omega d equals to omega n into 1 minus zeta square, omega into square root of 1 minus zeta square, and phi is tan inverse of 1 minus zeta square square root divided by zeta, or omega d by zeta into omega n. Anything works. Then capital K equals to 1 upon K. Yes, here capital K equals to 1 upon Ks. And then simply I have written the expression with the variable name x underscore t, that equation number 9. Now what we need to do is we need to differentiate this equation with respect to time. So the syntax for the differentiating is diff. Again, you can search for this command, help diff. So the differences is an approximate derivatives. This MATLAB function calculates differences between the adjacent elements of x. So there are different syntaxes for this. I have used dx different diff x of t divided by dt. The dt is the time interval. So here dt I have represented it as second vector minus second element of that vector minus the first element. So t of 2 minus t of 1. Now if you follow this way, then the time vector will actually be one element less than the that we have used before. The previously time element is 401. If I run this code, then time velocity, this element will be 400. So the way to write it as t of 1 is to end minus 1. So this time vector for velocity adjusted for differentiation. Then finally plotting the velocity response, that is figure 4. Plot t underscore velocity, the variable name that I have considered before, in x-axis, and then in the y-axis we have velocity. V is again the blue color, line width is 1.5, title velocity versus time by differentiating displacement response. Now let me run this code. And let us check whether are we getting the similar response of velocity by different methodologies. So this figure 3 represented by multiplying the displacement transfer function by s, and figure 4 we directly did the differentiation of dv velocity equals to dx by dt. So we observe that we get the similar response here. So there are different methodologies to obtain velocity. You can obtain either of these. Both methods are correct. Now that we are done with the velocity, let us go ahead with another approach of finding the position and velocity. Another methodology is state space approach. So what I'll do is I'll rewrite equation number 11 here. Let me go to the next page. So y double dot plus c by m into y dot plus ks by m into y 1 upon m into f. So this system is second order. This further means that the system involves two integrators. We know that the second order system can be represented by two first order differential equations. So let us define the state variables for those. X1 and X2 as, let us define X1 equals to, so let us define the X1 and X2 as X1 equals to Y and X2 equals to Y dot. What we'll do is we'll differentiate these two equations. We get X1 dot equals to Y dot, and Y dot is nothing but X2. Yeah, and then differentiate X2 dot equals to Y double dot. So Y double dot, we know it can be represented as, from this equation, Y double dot is, I'm writing here, Y double dot is F upon M minus C upon M Y dot minus Ks upon M into Y. So X2 dot equals to, I'll take 1 by M common, so minus Ks into Y. Y is nothing but X1. See, I'm transforming these equations to X1 and X2, new variables. Minus Ks into X1 minus C, Y dot is X2, Y dot is X2. So we write here minus C into X2 plus F. Now we have these two equations. This is equation 1, X1 dot. This is equation number 2, X2 dot. Now here this X1 dot and X2 dot, that is, there we are two integrators. We can also represent this in a block diagram. That is, let me just construct a block diagram for our transformed variables. So we have to integrate it twice. So this is the integrator symbol. We have to integrate it twice. Here it is X2 dot, and after it's integrated, it is actually X2, and after one more integrator, we get X1. If you see here, integration of X2 yields X1. Integration of X2 yields Y, and Y is nothing but X1. And here we have a summing block. So what is X2 dot here? X2 dot was 1 by M minus Ks into X1 minus Cx2 plus F. So here we have a block here 1 by M. Let me write here, this is plus, let me write this is minus. Here we'll take this signal C by M into X2. Here we have C by M into X2. I am just write here C by M, and then X2 is multiplied here. This is another summing block. I'll consider this as plus, and I'll consider this as plus. And another variable X1 that we have here, Ks upon M into X1. So I'll just multiply here with a block Ks upon M, which is X1, X1. And finally this goes to this summing block, and here it is minus, because here we have minus C by M into X2 and minus Ks by M into X1. And this is the input here, where input is multiplied by 1 by m, and this is the force. Now this transformed system x1 dot and x2 dot, that where there are two integrators, so it is represented by a block diagram. Now going further, here one thing I forgot to mention, here the output is x1, that is the displacement. So we can write these two equations in a matrix form. Matrix form as x1 dot and x2 dot here we have 0 1 minus ks by m, we have minus c by m into x1 x2 plus 0 1 by m to f. So if you see this matrix form carefully, these are the same equations. X1 dot equals to 0 into x1 plus 1 into x2 plus 0 into f, nothing but x1 dot equals to x2. Similarly, x2 dot equals minus ks by m into x1 minus c by m into x2 plus f by m, and y equals to cx. So if the output, if the measurement is only the displacement, we can take it as 1 0 c, and this is x1 and x2. And of course d is 0. For most practical applications, d is always more or less 0. So we have got A, B, C, D matrices. We know that the system state space form is represented as x dot equals to A into x plus B into u, y equals to c into x plus d into u. So here we have y equals to cx, this is 0. Now here A matrix is 0 1 minus ks by m minus c by m, and then B is 0 1 by m, C is 1 and 0, and of course D is 0. Now let us obtain the plots for position and velocity using the state space method in MATLAB. So we have plotted till figure number 4. The next is the state space approach. So here A is 0 1, and then next row minus k by m minus c by m, 0 1 minus k by m minus c by m, d is 0 1 by m, 0 1 by m, c is 1 0, c is 1 0, and d is 0, and d is 0. Now here the state space system can be formed by a syntax known as SS. Again, for more information about this syntax, help SS. So use SS to create real valued or complex valued state space models, or to convert dynamic system models to its state space model form. So the syntax is SS A, B, C, D. Let me show you what it is actually running. So if I run this code till state space, so here he has the MATLAB identifies the A matrix, B, C, and D. So this is a continuous time state space model. After this, we use the LSIM command as was discussed earlier. Here output we have y. I have defined the variable as y underscore ss, t as a time variable, and one more variable I have included here, x, that I'll let you know in a minute. And the syntax remains same, the system underscore ss under comma u comma t. So this is the syntax for using LSIM command. Then next I am plotting figure 5. So in figure 5 I am plotting both the position and velocity in order to avoid the cluster of figures. So I have used here subplot command. So here subplot 2 comma 1 comma 1. So here 2 represents number of rows, 1 is column, and the 1 represents the first figure. So here plot t comma t underscore ss comma y underscore ss, that is x comma y. Here I have represented as minus k, the lines, and the line width is again 1.5. I have commented this as of now. I'll explain in a minute. X axis we have time, y is position, title is spring mass damper system, grid is on, and the second plot in the same figure is subplot is 2 comma 1 comma 2. Here 2 is the second figure. So here plot t underscore ss, this is x of 2. Now this x of 2 actually represents velocity. If would have taken x of 1, it would again be a displacement. That is why I have considered here one more vector, here x. So here x is a vector which is having position, displacement, and the velocity. Now if you run this code for this figure 5, let me run the whole code again. Right. So this is figure number 5. Here we have position. This was velocity. Let me just rearrange it. So here we note that we state space method also, there is another methodology, state space method, which is giving the similar results for position and velocity. So there are different methodologies. You can opt for any, whichever you are comfortable with. Now we again observe here that both are similar plots, displacement and as well as velocity. Now let us proceed further. Now let us try to change the step input at 2 seconds. Let me write it here. So let us try step input at 2 seconds. At 2 seconds. Let us consider this as the first case. The step input here will be something like this. So this is actually 2 seconds and the force is same, that is 5 kgs, 5 kg force. And the second case will be impulse input. Impulse input till 0.1 second with a force of 50 kgs this time. So here till 0.1 second it will be 50 kgs and then it is 0. So this is 0.1 second and this the force is 50 kgs. Now how to plot these responses here in MATLAB? Let us see that. So here I have defined step force input, time I'm defining it again, lin space. There is another syntax for defining a time variable. So this is time from 0 to 10 seconds with 1000 points. Then F force I have written as the variable as F underscore step, that is 5 kgs force multiplied by 9.81 in newtons. And input, this input needs to be applied, that is force into when the time is greater than or equals to 2 seconds. So force into time greater than or equals to 2. So step 4 starting at t equals to 2 seconds. Now again the step remains, procedure remains same. Simulate the response using LSIM. I have represented the variable with step response for this condition case s system underscore step ss of a comma b comma c comma d, create state space system for step force, and again this is the output, y step, t step and x step, and these are the inputs LSIM, u step and time, and this I have considered as figure 6. Here I have considered three rows and one column, and this is the first figure. In the first figure I am representing t comma u. So in x-axis I have time, in y-axis I have input u to check whether I'm getting the intended input or not. K comma line width 1 comma 5, rest of the things remain same. Then subplot 3 comma 1 comma 2, this is the second figure of 3 figures, sub figures, and here it is plotted between time and the y step, that is one variable, first vector of this y step, and the third is the velocity x underscore step into 2. Now this of course will be second element of this x step. You try with by entering 1. So what you will actually observe is that is again the displacement vector. So if you want a velocity vector, you have to mention the second element of that vector. Now let me plot this. I am rerunning the entire code. Now see here, now this is the step input force which is applied at 2 seconds, and this is at 5 kgs, that is 50 newtons force. So this is the input that we actually intended for. And see this position, and this is the position, and this is the velocity response for mass spring damper system. So the position, it is settling around 0.07, approximately 0.07 meters, and here the velocity is again going to 0. So this was figure 6. Now let us proceed for an impulse response. How we can write a code for that. Impulse force input. So here impulse force magnitude is, I have assumed it as 500, 50 into approximately 10, 500 newtons, and duration is 0.1 second. So 0.1 second because the force is actually very high force for impulse in newtons, and this is only for short duration. So I have defined next as defined impulse force as a short pulse. So this input force will be applicable when impulse 500, when the time is less than or equals to the intended time duration, which is 0.1 second. Then again the process remains same. Simulate the response using the state space SS syntax, create state space system for impulse response, and these are the outputs: y impulse, t impulse and x impulse, LSIM, and rest of the things remain same. Now let me plot this. Let me run again the code. Now this is figure 7. Now see here, the force is actually 500 newtons for the first 2.1 seconds, and then it is 0. So here again we observe that now since the input is actually 0 here, so the displacement comes down to 0 and the velocity also comes down to 0. So what we can actually infer from this, with these plots we can easily say that the system is stable. And there is another methodology also that we can infer the system stability. If you remember that we have obtained a matrix we know that the system stability could have been easily checked assessed by checking eigenvalues of A matrix. Since we already obtained eigenvalues of A matrix, now before we check for the roots, we know that for the underdamped case, so for underdamped case, we know its zeta should be less than in between 0 to 1. Let us check how much is zeta. So here zeta is 0.2647, which is less in between 0 to 1. So here zeta is 0.2647. So the roots, we know the roots will obviously be complex conjugate. So that we can check directly in again in MATLAB. I've already entered the command. Then the syntax to check the eigenvalues is to EIG of A, and here we obtain minus 1.63 5 plus or minus 5.95 62 I. So here, since the real part is negative, so without plotting anything, we can easily say that the system is stable. This further means that any bounded initial disturbance will eventually decay to 0 over time. That is what we checked in these figures. When there was an initial disturbance or the force for 0.1 second, that is impulse force, the system is coming back to its equilibrium position. Similarly, in figure 6, with a different control input, a different step input, again the system is coming to its equilibrium point and the velocity is coming to 0. So learners are encouraged to plot these responses by yourself. So with this, we end the topic on simulation of a mass spring damper system in MATLAB. In the next lecture, we'll be taking a different example of pendulum system, but this time we'll be simulating in Simulink. Thank you.